This is Audible.
Survival. Evolutionary Rules for Intelligent Species Survival. Written by Samuel Lane. Illustrated by Sherry Wang. Narrated by Nathaniel Asher. Introduction. The struggle for life and survival. Can Homo sapiens survive, or is extinction inevitable? After more than 4 billion years and multiple mass extinctions, intelligent species finally evolved on Earth. What prompted this? Was it inevitable? There are many opinions, but the only explanation that should really matter is the one that can be found in the history of evolution's struggle to maintain life in a universe ensnared in a perpetual cycle of birth, life, and death. From an evolutionary perspective, it seems as if the entire reason for the existence and evolutionary journey of an intelligent species is to mature past the point of self-extinction and become capable of surviving the universe's existential threats. Put simply, to keep life alive. This book explores the possibility that intelligent species emergence was an evolutionary response to the universe's endless propensity for destroying life, and the roles of climate change and Homo sapiens in that response. Homo sapiens evolved in a universe in the grip of an endless cycle of birth, life, and death. Notwithstanding, evolution found a way to perpetuate life by evolving species capable of reproducing themselves. Evolution has managed to get life going on planet Earth and has kept it going ever since, repeatedly jump-starting life in the face of numerous mass extinctions. Yet after all of this effort to evolve and sustain life, species survival seems to remain at the mercies of the universe. Even after surviving for millions of years, species like the dinosaurs could do nothing to avoid extinction at the hands of this universe. That colossal meteorite impact that put an end to more than half of the Earth's species, including all non-avian dinosaurs, was felt across the evolutionary species universe and may have changed the course of evolution forever. It certainly got evolution's attention. It's possible that the evolution of an intelligent species that can choose its own fate, survival, or extinction, might have been evolution's response to the inability of otherwise successful species to save themselves when confronted with such random galactic, solar, or planetary scale existential threats. It is unsurprising that it wasn't long, in geologic time, after the elimination of the dinosaurs, widely believed to have made the rise of mammals possible, that intelligent species in the genus Homo, including hominins and eventually Homo sapiens, entered the picture. About 6 million years before Homo sapiens showed up, evolution began grooming and winnowing a clutch of emerging hominin species. Most went extinct, but some survived and eventually gave rise to what we now know as Homo sapiens. One evolutionary question might have been whether one of these intelligent species would survive past the point of self-extinction to evolutionary maturity, be able to migrate from planet to planet and star to star, and eventually perhaps to other galaxies if necessary to survive. No matter what one might believe about why we are here, then, intelligent species evolution might be nothing more or nothing less than evolution's response to the universe's existential threats to the survival of life. Evolution, it seems, wanted to find a way for life to survive, whatever the universe might throw at it, and the evolution of mature intelligent species might well have been the answer. So far. So, more than 6 million years ago, evolution set out to evolve a new kind of animal species that would be free to choose its own evolutionary destiny. A species that would in time evolve the capability to transcend and largely replace the instincts that control the behavior of all other animal species. A species with an emergent intelligence that would enable it to evaluate potential outcomes and make choices to shape its own evolutionary outcome in ways no prior species could. A species that could make choices so far-reaching that it could potentially, perhaps inadvertently, bring about its own extinction and the extinction of numerous other species. Or instead, make choices to mature beyond the point of self-extinction to evolutionary maturity. No prior species could do anything other than follow the integral biological routines endlessly executing in its brain. None could reprogram itself or do anything beyond its natural instincts. But with this fixed programming also came an advantage. Such species never had to ask, "Why am I here?" or wonder about their purpose in life. They lacked the intellectual tools to do so, and that purpose was hardwired inside them. Every area of their lives had been pre-programmed. Nor were such species going to come up with the means to drive themselves or other species to extinction. They would never develop the ability to change Earth's atmosphere, precipitate global warming, poison the food chain, or hunt or fish other species to extinction. They could never enslave others of their own species, nor wage global warfare against them. Such species had no need to grow to evolutionary maturity as they evolved. They were as fully matured as they would ever be. Homo sapiens, though, would need to reach evolutionary maturity just to survive and avoid self-extinction. The attributes that enabled an intelligent species to transcend the limitations of prior species, intelligence and the freedom to choose its own evolutionary destiny, were simultaneously its greatest strengths and its greatest weaknesses. With intelligence and the freedom to choose came the awesome responsibility to choose to grow to full evolutionary maturity, a challenge no prior species had ever had to face. Like human infants, intelligent species require guidance and time to grow into full evolutionary maturity. Or, like immature adult humans, they will self-destruct and take themselves out, and potentially all other species with them. And that, it would seem, is the survival struggle 21st century Homo sapiens now confront. Whether we are aware of it or not, our species, Homo sapiens, is engaged in an evolutionary battle for its very survival, and the enemy it faces is within. Homo sapiens' freedom to choose its own evolutionary outcome, and the intelligence that comes with it, can be used to either reach that level of evolutionary maturity that other species begin with, or to imagine, innovate, and create the means of its own extinction. The evolutionary pattern at work here is uncomplicated, and innovation has little if anything to do with it. Notwithstanding its ability to adapt and innovate, an intelligent species must reach evolutionary maturity, or it will go extinct. No maturity, no survival. It's that simple. The greatest threat to Homo sapiens' survival is not a meteorite impact, not a Death Star, not WMDs, or weapons of mass destruction, and perhaps not even AI, or artificial intelligence. Though possible, most of these are unlikely in the short to intermediate term, and others, such as WMDs and AI, are but symptoms of the real threat. The real threat, the clear and present danger, is Homo sapiens itself. But alas, the search for evolutionary maturity and survival is not exactly a topic that preoccupies Homo sapiens today, and therein lies the problem. This may be due to a lack of a true understanding of Homo sapiens' reason for being, and potential role in the greater evolutionary scheme for life in the universe. It may also be due to not understanding the dire consequences of getting the relationship between its survival and its maturity wrong. Homo sapiens appears to have conjured up its own reasons for being and missed those landmarks that might have led it in a direction more consistent with survival and evolutionary maturity. Today, humans have arrived at a point where a handful of men are literally capable of extinguishing our species. Fortunately, it does not appear that evolution has left this intelligent species to fend for itself. It may have provided numerous survival rules and patterns, assembled here into a survival manual, a species survival maturity model, to show the way, a kind of yellow brick road that runs past the point of self-extinction and on to evolutionary maturity and survival. In the following chapters, I attempt to delineate that yellow brick road and identify the landmarks along the way, making it easier to follow in the hope that our species may yet notice and change direction before it's too late. This is a book about survival. It asserts that in a universe ensnared in endless repeating cycles of birth, life, and death, evolution appears to be firmly on the side of life and intelligent species survival, and consequently, extinction is not inevitable. It explores the backstory, why, from an evolutionary perspective, an intelligent species, like Homo sapiens, may have evolved in the first place, and what it needs to do to continue to survive in such a universe. It explains the yin and yang relationship between intelligent species survival and its attainment of evolutionary maturity. It depicts the struggle to mature past the point of self-extinction to reach evolutionary maturity in terms of an evolutionary survival game of life that may well have begun more than 5 million years ago with the evolution of the genus Homo, possibly Earth's first intelligent species, and forebears of Homo sapiens. It identifies what appear to be survival rules and patterns that evolution may have strewn like Hansel and Gretel's breadcrumbs, instructions for intelligent species to follow in order to play to win and thereby survive. And it organizes these into a species survival maturity model. It shows the potential link between reaching evolutionary maturity and developing the abilities necessary to survive existential threats, such as those that took out the dinosaurs, and achieving interplanetary migration. It concludes with a peek at where Homo sapiens evolution could be headed, extraterrestrial mature intelligent species evolution, should it manage to mature past the point of self-extinction. It also looks at the potential opportunities Homo sapiens might well have to collaborate with evolution in the spread of mature intelligent species life across the galaxy. And finally, it considers what could be in store should Homo sapiens fail to mature. It explores which of these two outcomes Homo sapiens is likely to choose and why: maturing past the point of self-extinction to survive, or failing to mature and going extinct. These are the only possible outcomes in this evolutionary game of life. Choose well. Part 1. Evolution versus the universe, and the struggle for life and survival. Life and survival versus death and extinction. When it comes down to the question of species extinction versus species survival, evolution appears to have always sided with species survival, endowing species with the ability to survive and persist through reproduction, and to preserve their survival through migration. Viewed from this perspective, it begins to look like an interplay, perhaps even co-opetition, between the universal forces of birth, life, and death on one hand, and evolution on the other, with life and survival as the prize. When this interplay and delicate dance is traced back through Earth's history, it begins to seem unbelievable that life somehow survived being handed off back and forth from one of these galactic forces to the other. It is even more amazing that order was lurking deep inside the incomprehensible chaos of the universe and the early days of the Earth. Despite seeming like a purposeless process, evolution comes across as a type of order that brought life and consciousness into the world. And through evolution, life managed to find a way. Paraphrasing the words of Nobel Prize-winning Austrian physicist Erwin Schrödinger, evolution and thereby life sucked order from a universe of disorder. There is an untold story here of the heroism and persistence of the evolutionary process, a seemingly mindless repeating universal pattern that drives order and life in the midst of a universe of seeming chaos, from microbial to complex animal to intelligent species life. Across galactic timescales, possibly across solar systems, galaxies, and universes, through innumerable extinction events on Earth, evolution enabled and sustained life and survival over death and extinction. From this perspective, one can no longer think of evolution as a detached and disinterested process. Instead, it becomes a set of repeating universal processes that create a repeating universal pattern. And in the midst of a universe seemingly consumed by chaotic processes, enables order in the form of life and survival over death and extinction. Chapter 1. Earth, the planet evolution terraformed for life and survival. Can you recall how it felt the first time you saw the photo Earthrise, taken by astronaut William Anders during the Apollo 8 mission in 1968? According to NASA, they also became the first to look back at their home planet and see the entire world in one glimpse. Like seeing oneself in a mirror for the first time, after 300,000 plus years or so evolving to our present state, Homo sapiens had finally discovered Earth. The image of our blue planet far beneath those astronauts has had an everlasting impact on our collective consciousness. For the first time, we were yanked away from the cares of our individual lives to collectively gaze in awe and wonder at the Earth from the perspective of the moon, each of us slowly realizing that we stood somewhere on that rotating surface along with everyone else, as it receded into insignificance, becoming like a pale blue dot, barely visible when seen from beyond Pluto, 6 billion kilometers out, as photographed by Voyager 1. We are trapped here, adrift like polar bears driven by erratic currents on a chunk of ice, endlessly rotating around the sun, the lone star in Earth's solar system, one among 300 billion stars in the Milky Way galaxy, itself just one of 200 billion galaxies. And yet, for most of the 300,000 years or so we have been evolving, we hadn't realized how lonely and precarious and how precious our existence has been. Judging from where we are heading, we still haven't. But while it was for us the very first time we had actually seen the Earth floating in the darkness of space, we might not have been the only ones looking. Over the last 4 billion plus years, evolution has been keeping watch over the Earth like a hen over her chicks, getting it ready to evolve and sustain complex animal and intelligent species life. And while we may not have realized how lonely, precarious, and precious our existence has been, evolution would no doubt have known all along. It is amazing how different that pale blue dot seems when viewed from this perspective. Perhaps we aren't alone. Perhaps we never were. During the course of human evolution, we have learned the value of living in communities and the benefits of having neighbors who can lend a helping hand in times of trouble. But where are Earth's neighbors? Do we even have neighbors? Where and how do we even begin to look? The distances to planets in our solar system are mind-boggling. This is a whole new challenge confronting our species. Within the span of 30,000 years, our ancestors traveled from humanity's ancestral home in Africa across continents and oceans until they had migrated to every corner of the planet. But until now, we had never ventured away from its surface to visit another planet. We have been to the moon, but in astronomical terms, the moon is in our own backyard, and we found no trace of life there, let alone intelligent life. The distance from Earth to the moon on average is about 238,855 miles, or 384,400 kilometers. In contrast, the distance to the Sun is about 92,900,000 miles, or 149,600,000 kilometers, or 1 astronomical unit, AU. For good reason. Except for NASA's Parker Solar Probe to study the Sun, we have no plans to go there anytime soon, even though we could use some of the fusion energy that powers it. How about Mars? There's lots of talk, plenty of interest, and even some plans for going to Mars. That's a distance of about 0.52 AU, which at approximately 78,340,000 kilometers, or 48,678,219 miles, is no road trip either. According to NASA, a manned vessel would take roughly 6 months to travel to Mars, and another 6 months to travel back. In addition, astronauts would have to stay from 18 to 20 months on Mars before the planets realigned for a return trip. In all, the mission would take roughly 2.5 years. In other words, if we have any neighbors, don't expect to meet them in the near future. So, though the search continues, we have found no intelligent life in our solar system so far. For perspective, it's important to remember that the technologies needed to search for intelligent life are less than 200 years old. It was only in 1844 that Samuel Morse sent his first telegraph message from Washington, D.C. to Baltimore, Maryland. By 1866, just 22 years later, a telegraph line had been laid across the Atlantic. Similarly, television was first successfully demonstrated in 1927. We are so immersed in technology today that it's easy to forget that in less than a single lifetime, we have gone from the Wright brothers' 4 brief flights in 1903 to landing men on the moon in 1969. As Brian Cox says in Human Universe, Homo sapiens has gone from ape man to spaceman in less than 250,000 years. It was not until the middle of the 20th century that we had the computers and radio telescopes that allowed us to begin looking for extraterrestrial intelligent life. Now, after more than 60 years of searching for any sign that there are other intelligent species out there, the SETI, Search for Extraterrestrial Intelligence, program has come up with nothing. Not just in our solar system, but also across several star clusters in our galaxy. Nada. But SETI continues to look and listen. Can this conspicuous absence of other emerging technological species in our solar system, and as far as we know, our galaxy, be purely accidental? And not only have we yet to find another emergent intelligent species elsewhere in our galaxy, there are no other hominin species left on Earth either. No Homo erectus, no Neanderthals, not even Homo floresiensis, the hobbits who hung around until about 18,000 years ago. Are these two things purely random, or could they be somehow related? If the evolutionary goal is the survival of at least one emerging intelligent species, then a not-so-subtle hint might be the trouble Homo sapiens have had getting along with each other, let alone other intelligent species. And is the location of Earth, as a place on which to evolve complex animal and intelligent species life, also accidental? From anyone's perspective, finding a quiet corner of the galaxy to evolve such life forms, as far as possible from the potential galactic mayhem of black holes, gamma ray bursts, and other agents of death that, however inadvertently, can quickly and unceremoniously snuff out life, seems an eminently reasonable evolutionary choice, even if random. Imagine what it would have been like for early humans. Imagine, say, you lived somewhere in Canada and suspected other humans might live somewhere in Australia. Imagine, too, a world in which you had no means of transporting yourself from Canada to Australia, nor any means of contacting that neighbor. In fact, if a message somehow got through, there would be no way of knowing it had been received, let alone understood. Finally, consider the odds of communicating if it took 50 years for a message to get to Australia, another 50 for a reply to be received, when your life expectancy was just 50 years. As an analogy of our current plight, this isn't overstated, and it is definitely not funny. Should something really bad happen in Canada? No, not like the Alberta tar sands bonfire, as bad as that was. I mean really bad. Bad like what happened during the Mesozoic era, about 65 million years ago, that left Mexico's Chicxulub impact crater buried underneath the Yucatan Peninsula. Yes, that big bad asteroid, roughly 15 kilometers or 9 miles wide, that hurtled into Chicxulub, Mexico, and took out more than 50% of the species on the planet, including the dinosaurs that had been roaming the Earth for about 165 million years. If something like that were to happen again, and it could, we don't have the technology to deflect a potential killer rock with Earth in its crosshairs. We couldn't expect, say, Vulcans to come to our rescue. If they exist, they would not have found us as yet, as we still have not developed warp drives. In fact, we would be like those polar bears, floating on a lone chunk of sea ice. No one would be coming to look for survivors, as far as we know. Like the dinosaurs, that would be it for us. Millions of years later, some subsequent species, perhaps humanoid, perhaps not, might well be heating their homes by burning our fossilized remains, just as we have done with the fossilized remains of other species, dinosaurs among them. But if not the Vulcans, certainly evolution might have been looking when the dinosaurs were taken out. In fact, that event, as this book suggests, might have been the reason we are here. So there might not be neighbors in our solar system to come to our aid. But might there be intelligent technological species elsewhere in the Milky Way galaxy, our galaxy? Many scientists think the answer has to be a resounding yes, based on the number of Earth-like planets orbiting their stars in the habitable zone, and the knowledge of how intelligent life came into being on Earth. The habitable zone, sometimes referred to as the Goldilocks zone, is the orbital distance from a star that allows liquid water to exist on a planet's surface. Scientists now estimate that there are about 300 billion stars in the Milky Way galaxy. Extrapolating from the number of planets detected by Kepler Space Telescope, Kepler's limited field of view is 1/4% of the visible galaxy, there might be as many as 100 billion planets orbiting those stars, of which about 50 billion are believed to be rocky planets like Earth. In November 2013, based on Kepler space mission data, astronomers reported that there could be as many as 40 billion Earth-sized planets orbiting their stars in habitable zones in the Milky Way, 11 billion of which may be orbiting Sun-like stars. The following table, courtesy of NASA, shows the number of Earth-like planets discovered through May 2016. Given such a large number of Earth-like planets orbiting Sun-like stars in the habitable zone, scientists have concluded that life may have started on some of these planets as well. But what are the conditions that must have existed on Earth for life to evolve? While the galaxy is thought to be nearly as old as the universe, some 13.8 billion years old, our solar system is thought to have formed only about 4.6 billion years ago. Single-celled life is believed to have sprung into existence on Earth as soon as the conditions made it possible, some 3.5 billion years ago. Homo sapiens, the species, has existed for 300,000 years or so, and has had technology with the ability to contact other intelligent species for little more than the last 100 years. Yet, to find other intelligent species, they must first exist. How long should it take for an intelligent technological species to evolve? It essentially took about 4 billion years for intelligent life to evolve on Earth. Since many of these stars with Earth-like planets orbiting in the habitable zone are billions of years older than the Earth, then intelligent technological civilizations could have arisen billions of years ago on at least a few of these. But if that is so, one must ask, as Enrico Fermi did, where are they? The so-called Fermi paradox. Why is there no answer to the SETI signals? And why has nobody tried to make contact, as the Vulcans did in the Star Trek movie First Contact? Where have all these intelligent, technological, communicating civilizations gone? Some scientists believe that while life may have arisen on many of these exoplanets, intelligent, technological life with the ability to seek out and communicate with others might occur so rarely and last so briefly as to preclude opportunities for contact between intelligent species. Scientists call this the Great Filter Theory. It's a notion that's often invoked to explain why we've never been contacted or visited by extraterrestrials, although the UFO community might disagree with that conclusion. Some astrobiologists theorize that all advanced technological civilizations hit an insurmountable developmental wall and self-destruct, a topic this book explores in some detail. But if so, why would an intelligent extraterrestrial species go extinct? And how could that be avoided? What was it about their evolutionary journey that led to their demise? Were they destroyed by, or in spite of, their own technological advancements? Did they make it that far along the evolutionary journey only to be wiped out by a planetary or interstellar catastrophe, as the dinosaurs were even after 165 million to 175 million years of roaming the Earth? Compared to the dinosaurs, our species, Homo sapiens, has only been around for about 250,000 years. Notwithstanding, there are those who argue that Homo sapiens might be the only extant intelligent species, not only in our solar system, but in the entire Milky Way galaxy. They base this view on how incredibly lucky Homo sapiens seems to have been to evolve at all. But that's a conclusion that is no doubt reached from a purely anthropocentric perspective, and it's one with which evolution might beg to differ. The sobering question we should all be asking ourselves is, lucky or not, will humans, who began only 200 years ago to develop the kind of technology that enables a search for other advanced alien species, continue to be lucky and get past this developmental wall, this survival wall, or go extinct? But does survival of an intelligent species come down to just a series of lucky breaks? Is there really some event that needs to break our way, such as dodging the next dino-destroying size rock that might be headed in our direction? Are there planetary, solar, and galactic speed bumps that work against getting over that so-called insurmountable developmental wall? Or is there some sort of species survival maturity model, as yet unknown, a path to survival if followed, with which Homo sapiens needs to align its evolutionary journey? The question this book explores is, can we? will we survive? While scientists have not yet been able to prove that intelligent, technological, communicating alien species exist on other Earth-like planets, or have already come and gone, we know for certain that the dinosaurs came, hung around on Earth for 165 million years to 175 million years, and went. Can we do better than the dinosaurs? Is there even a way to know? Given our current trajectory, many people would agree that it's more likely than not that we'll eventually do ourselves in. Indeed, it's difficult not to be pessimistic when considering Homo sapiens' prospects. For those who think Homo sapiens can survive, comfort can no doubt be found in the words of the late Stephen Hawking, one of the greatest minds, if not the greatest, to come along in a lifetime. He said, "It is clear that we are just an advanced breed of primates on a minor planet orbiting around a very average star in the outer suburb of one among 100 billion galaxies. But, ever since the dawn of civilization, people have craved for an understanding of the underlying order of the world. There ought to be something very special about the boundary conditions of the universe, and what can be more special than that there is no boundary? And there should be no boundary to human endeavor. We are all different. However bad life may seem, there is always something you can do and succeed at. While there is life, there is hope." So, what is it we need to do or change as an emerging intelligent species to scale that insurmountable developmental barrier and survive? If there is such a thing as a species survival maturity model that can help our species survive, we owe it to ourselves to find it. Evolution began the incubation of complex animal and intelligent species life here on Earth, a planet in an obscure arm of the Milky Way galaxy, far from any neighbors, far from its center, out of the way of most of the galactic mayhem, perhaps to give life a better chance at survival. It was going to take evolution most of 4 billion years to prepare Earth for the emergence of possibly its first line of intelligent species in the genus Homo, 6 million years ago, whence came the line of hominins and, 300,000 years ago, Homo sapiens. It would seem beyond strange if after going to such lengths, evolution didn't leave intelligent species, if not a user manual, at least a few breadcrumbs, like in the Hansel and Gretel fairy tale, to guide the way to survival. Homo sapiens' quest, it would seem, would be to find and follow them, all the way to survival. The purpose of this book is to identify them, if they exist. Going forward, we will attempt to identify the evolutionary laws or patterns that affect intelligent species survival, as well as those that hasten their extinction. By reviewing early Homo sapiens' survival history, we hope to see how these patterns and laws facilitated or impeded migration out of Africa. Further on, we will attempt to gather, step by step, the components, then go on to assemble what may well be an intelligent species survival roadmap, a species survival maturity model. Chapter 2. Does the universe come with evolutionary species survival mechanisms? Are there evolutionary rules for intelligent species survival? The universe offers a vast range of laws, patterns, and models that enable an understanding of the most massive of multiverses, galaxies, and solar systems, and the most minute of cells, atoms, and subatomic and quantum particles. Wouldn't it be surprising if such a universe did not also include laws, patterns, and models that enable an understanding of the processes that drive intelligent species survival and extinction? Wouldn't it also be surprising if such a universe did not show just as clearly what models, laws, and patterns an intelligent species must follow to escape extinction and ensure its survival. The universe is understandable because it follows a model. Homo sapiens evolved in a universe that science has shown is governed by a set of laws. In his book, The Big Picture, cosmologist Sean Carroll says, "A law of physics is a pattern that nature obeys without exception." Given the state of the universe at any specific time, these laws specify how the universe would develop from that moment forward, or its history up to that point in time. Biological processes are also governed by universal laws, the laws of physics, chemistry, and quantum particle laws, and therefore might be just as deterministic as the orbits of the planets at some levels, and as probabilistic as the laws governing quantum phenomenon at others. Indeed, according to quantum physics, says Stephen Hawking in his book The Grand Design, nature does not dictate the outcome of any process or experiment, even in the simplest situations. Rather, it allows a number of different eventualities, each with a certain likelihood of being realized. It is, to paraphrase Einstein, as if God throws the dice before deciding the result of every physical process. Hawking continues, "The laws of nature determine the probabilities of various futures and pasts rather than determining the future and the past with certainty. It is precisely because of the orderliness and predictability that result from these patterns and laws that Homo sapiens can send space probes and satellites to survey the other planets of our solar system or rendezvous with comets. It is because of them that we know with certainty that the next solar eclipse would have occurred on July 2nd, 2019, and that Halley's Comet will again appear in Earth's vicinity in 2061. Similarly, because of such patterns and laws, biologists are now able to conceive of an ecosystem as a society of organisms interacting with one another through a food chain. Doctors can see the body as a collection of organs communicating with one another through the nervous and endocrine systems, and microbiologists can picture life in cells as a society of macromolecules bound together by a complex system of communications regulating both their synthesis and their activity. In the words of Sean Carroll in his book The Serengeti Rules, every cell contains a society of molecules, every organ a society of cells, every body a society of organs, and every ecosystem a society of organisms. And understanding the interactions within each of these societies has been the primary aims of molecular biology, physiology, and ecology. Given that there are rules, patterns, and models that govern the universe and regulate the cells of the body and number and type of animals in an ecosystem, what then are the rules, patterns, and models that must also exist to guide an intelligent species to survival? What do nature's probabilities say about intelligent species survival? Is there such a thing as a species survival maturity model that would enable an intelligent species, such as Homo sapiens, to survive if followed? Are there planetary or even galaxy-wide patterns that work to accelerate survival, or serve as speed bumps that unintentionally slow or block survival? If a bacterium, barely visible in a microscope, without a nervous or endocrine system, has been shaped by evolution to know how to make the right enzyme for whatever sugar it encounters, wouldn't evolution have endowed an emergent intelligent species with the ability to make the right choices to survive? Yes and no. Yes, because the evolutionary rules and patterns are more than likely there, and will lead an intelligent species to survival if discovered and followed. No, because unlike bacteria that evolved hardwired programming to internalize those rules and patterns, and thus know exactly how to make the right enzyme in response to a specific chemical, an emergent intelligent species has to first discover those rules and patterns, what we now call chemistry and microbiology. It must then go on to write its own mental programs on how to apply them in order to survive. The existence of these universal natural laws, patterns, and models, which we now know predate intelligent species evolution, is by itself no guarantee they'll be discovered and used to aid intelligent species survival. Just to be able to understand and do what non-intelligent but pre-programmed species do routinely must be anything but easy, as it took evolution 4 billion plus years to get Earth's first intelligent species from slime to ape man to spaceman, modern Homo sapiens. A cursory review of the history of science and early intelligent species discovery and application of these laws documents the emergence of a nascent intelligent species that evolved from an instinct-driven, tree-climbing ape on all fours to a bipedal, erect, intelligent, self-aware spaceman. The journey took several million years, involved the evolution and extinction of multiple hominin species, and the rise and fall of innumerable prior Homo sapiens civilizations. By the look of things, Homo sapiens might still have a long way to go. For almost the entire 300,000-year existence of our species, Homo sapiens discovered relatively little about the laws of the universe and nature, let alone the evolutionary patterns and laws that can potentially guide intelligent species survival. Paraphrasing Sean Carroll, we gathered fruits, nuts, and plants, hunted and fished for the animals that were available, and like the wildebeest and zebras on the Serengeti, we moved on when the resources ran low. Even after the advent of farming and civilization and the development of cities, Homo sapiens remained vulnerable to the whims of the weather, climate change, and still is, and to famine and epidemics. It was only in the last 100 years that knowledge of these universal and natural laws accelerated. During those 300,000 years, Homo sapiens was controlled mostly by biology, but in the last 100 years or so has begun to be controlled more by its intelligence and has taken control not only of biology, but of most areas that impinge upon Homo sapiens' existence. Well, almost. First came knowledge of the universe and physical laws that regulate how the universe works. Then followed knowledge and awareness of the laws of nature that enabled the move away from hunting and gathering to agriculture, which in turn led to the formation of cities and towns. As knowledge in these and related areas grew, so did our ability to take control of our destiny. This increase in knowledge turbocharged the development of Homo sapien civilizations. But even as our knowledge and abilities grew in these areas, knowledge of the evolutionary laws and patterns that can guide an intelligent species to survival appears to have gotten lost along the way. Modern Homo sapiens has emerged with astonishing capabilities, but the price paid for them is lack of growth in the one area that will matter most for its survival: evolutionary maturity, the ability of an intelligent species to mature beyond the point of self-extinction. A bacterium knows how to make the right enzyme for whatever sugar is available, but it also knows when to stop. Homo sapiens has learned to apply many of the laws of nature, but unlike that simple bacterium, has yet to learn when to stop. What's more, Homo sapiens has yet to discover and implement the evolutionary laws and patterns that will ensure an intelligent species' survival. And in the absence of this knowledge, can our species survive or go extinct like the dinosaurs? Starting in this chapter and throughout this book, we will go back to the beginning and look at various events in the life story of our forebears over geologic time. We will consider the emergence of what might have been Earth's first intelligent species and pick up the trail to find out how our species evolved and the methods evolution seems to have employed to guide intelligent species to maturity. Along the way, we'll try to identify any survival patterns, rules, and models that emerge, attempting to keep a wary eye on evolution and try to decipher, if possible, what might have led to the evolution of intelligent species. Homo sapiens was neither the original nor the only species of hominins that came out of Africa. In fact, Homo sapiens, the last of the hominins, is just the most recent in a long line of hominin species that evolved, thrived, and then went extinct. There's no guarantee we won't go extinct too. Extinction is a normal part of life in the universe, and despite the high regard in which we currently hold ourselves, we too might one day be replaced by a superior version of our own species, as Homo erectus was by us. Perhaps we will be supplanted by Homo machina, with a biology that is just the right mix of man and machine for interplanetary and interstellar travel. But more about this later. From the fossil record, it appears some species of hominins survived longer than others. On average, they lasted between 900,000 and 1 million years before going extinct. 2 million years ago in Africa, several species of human-like creatures roamed the landscape. Our own species appeared around 300,000 years ago, at a time when several others existed. But as recently as 30,000 years ago, there were only 4 other hominin species around: the Neanderthals in Europe and Western Asia, the Denisovans in Asia, about whom not much is known, the hobbits from the Indonesian island of Flores, and more recently discovered Homo luzonensis, found in a cave on Luzon, the largest island in the Philippines, who lived some 50,000 to 80,000 years ago when there were multiple archaic humans. Today, only we remain, which raises the question, how did Homo sapiens manage to survive when all others, even those closest to our species, have gone extinct? The answer might be quite different if it could be asked from evolution's perspective, a perspective that we, as a species, might do well to ponder. The following is an incomplete timeline of known species of hominins going back nearly 6 million years. The hobbits, Homo floresiensis, could have survived until as recently as 18,000 years ago, and according to geological evidence, they may have been wiped out by a large volcanic eruption. Living on one small island, as they did, makes a species much more vulnerable to extinction when disaster strikes. And that might also turn out to be true of Homo sapiens, who now live on a single planet, this island, Earth. It certainly turned out to be true for the dinosaurs. The first discovery of Neanderthals was in the mid-19th century, at a site in the Neander Valley of Germany. Neanderthal means Neander Valley in German. Their earliest ancestors, called archaic Homo sapiens, evolved like all hominins did in Africa and migrated outwards into Europe and Asia. Neanderthals migrated to Eurasia long before humans did, and lived as far north and west as Britain, through part of the Middle East and east to Uzbekistan. Estimates put the peak Neanderthal population at around 70,000, though some scientists believe the number was drastically lower, with as few as 3,500 females. They lived as hunter-gatherers and scavengers until about 30,000 years ago, when they disappeared from the fossil record. For the last 10,000 years of their existence, Neanderthals shared Europe with Homo sapiens, and apparently led fairly similar lifestyles. No one knows exactly why Neanderthals went extinct and humans survived. Some scholars theorize that gradual or dramatic climate change led to their demise. They had lived during the Ice Age, often taking shelter from the ice, snow, and otherwise unpleasant weather in Eurasia's plentiful limestone caves. They struggled more with a changing climate than Homo sapiens did, and there were very unfavorable climatic conditions at the time of their extinction. Others blame dietary deficiencies. Some theorize that humans killed the Neanderthals. Until recently, the hypothesis that Neanderthals didn't go extinct, but simply interbred with humans until they were absorbed into our species was popular. And studies reveal that in European and Asian populations, between 1 and 2.5% of human DNA comes from Neanderthal DNA. Why did Homo sapiens survive while other hominin species went extinct? What might have been the hurdles Homo sapiens successfully negotiated that enabled its survival? Perhaps the more general question is, what are the evolutionary factors that select for survival when lacking them leads to extinction? When viewed from this perspective, it also becomes useful to ask which of these survival factors are due to nature or nurture. What we might think of as nature are those that are innate to a species, the size of their brains, and how smart, innovative, and naturally adaptable they are. And what we might think of as nurture are external factors that would include planet-wide disasters, such as an asteroid impact, remember the dinosaurs, glaciation or ice ages, and supermassive volcanic eruptions. Also, extreme environmental and climatic conditions, such as killer storms, floods, and droughts, might have made staying in familiar, ancestral areas untenable due to increasingly unsustainable or unavailable habitats, and increasingly inadequate and inaccessible food and water sources. And of course, there's also predation, as our ancestors were as often prey as they were predator. A lot has been made of the larger brain size and thereby the smarts and inventiveness of Homo sapiens, in contrast to some of the earlier hominins. But Neanderthal brains were as large as Homo sapiens, even thought to be larger, yet they went extinct. Neanderthals and possibly some earlier hominin species are believed to have developed language as well as art, as demonstrated by cave paintings in parts of Europe long before humans are thought to have arrived. So, could the naturally occurring innate capabilities, nature, have been so significant that they can account for Homo sapiens survival and Neanderthal extinction by themselves? If so, what can explain the survival of 7 species of great apes, 2 species of chimpanzees, 2 species of gorillas, and 3 species of orangutans, which few would consider innately more capable or smarter than the Neanderthals or other hominin species? It seems hard to conclude, then, that Homo sapiens' innate abilities, however superior and which must have conferred some necessary evolutionary advantages, could have been sufficient to ensure survival. Consider the dinosaurs again. Their extinction appears to have had nothing to do with how big their brains were, or any other innate abilities. So, given the environment and changes in climate that were occurring at the time, it seems more likely that external factors played a much greater role when it came to the survival of Homo sapiens. What was the Earth like when Homo sapiens were leaving Africa? This becomes apparent when one examines the prevailing environmental and climate conditions thought to have accompanied early human migration out of Africa, and its impact on Homo sapiens evolution. It is believed that all later species of the genus Homo evolved during the Pleistocene epoch, 2.6 million to 11.7 thousand years ago. This was generally a time of more extreme world cooling and recurrent glaciations, or ice ages. During the coldest periods, global temperatures dropped by about 9 degrees Fahrenheit or 5 degrees Celsius, and long-lasting ice sheets spread out from the poles and high mountains. Between the 4 or more major glaciations of the Pleistocene, there were interglacial warming periods, when temperatures were similar to what they are now. Both the glacial periods and interglacial periods lasted tens of thousands of years. Some scientists believe it's likely the Earth is still in an interglacial period that began 10,000 to 12,000 years ago. The continents of the northern hemisphere were more affected by glaciations than those in the southern hemisphere, which generally remained mostly tropical and subtropical during the ice ages, though more humid. The coldest regions of the world became Arctic deserts. However, during the Pleistocene, the great deserts of North Africa and western North America were mostly grasslands, with large permanent lakes and abundant large-game animals. Sea levels during the coldest periods were as much as 450 feet, or 137 meters, lower than today, due to a substantial volume of the world's water being locked on the continents in 1/2 mile thick glacial sheets covering thousands of square miles. As a consequence, vast areas that are now shallow sea and ocean bottoms were exposed for thousands of years. Twice during the last ice age, lowered sea levels resulted in Siberia being connected to Alaska by a 1,200 to 1,300 mile wide, or 1,900 to 2,100 kilometers wide, corridor. Asian hunters are believed to have used this route to migrate into the Western Hemisphere to become the first Native Americans. Ever since our ancestors branched off the primate evolutionary tree millions of years ago, there have been drastic swings between moist and dry periods, as well as long-lived glacial freezes and thaws. It is highly likely that early humans had to survive an ice age. What is generally thought of as the last ice age, 12,000 to 110,000 years ago, came near to being a Homo sapiens extinction event. According to the genetic and paleontological record, earlier hominin species, Homo erectus and Neanderthals, migrated from Africa many thousands of years earlier, but Homo sapiens started to leave Africa only between 60,000 and 70,000 years ago. What set this in motion is uncertain, but it is highly likely that it had a lot to do with major climatic shifts, including, but not limited to, the eruption of a supervolcano, Mount Toba in Sumatra, also around 70,000 years ago. That may have led to a nuclear winter, a sudden cooling of the Earth's climate driven by the onset of one of the worst parts of the last ice age, that resulted in a 1,000-year ice age. These changes in environment and climate are evident to scientists in layers of sediment, each layer indicating changes in vegetation, moisture, the animals that were around, and other survival challenges faced by our predecessors. There is some evidence that the ice came and went in regular cycles, driven by changes in Earth's orbit. The cool temperatures of the Quaternary period, the most recent glacial period, are believed to have left their mark on our species. Cold snaps would have made life extraordinarily difficult for our African ancestors, and indeed, the genetic evidence points to a sharp reduction in population size around that time. In fact, the human population likely dropped to about 2,000 individuals. As a species, Homo sapiens appears to have been holding on by a thread. Shortly after Homo sapiens first evolved, the harsh climate conditions nearly extinguished our species, said Professor Curtis Marine of the Institute of Human Origins at Arizona State University. Professor Marine discovered ancient human artifacts in the isolated caves around an area known as Pinnacle Point in South Africa. According to Marine, the caves contain archaeological remains going back at least 164,000 years. Recent finds suggest the small population that gave rise to all humans alive today just happened to survive by exploiting a unique combination of resources along the southern coast of Africa, said Marine. The strip of land on Africa's southern coast, around 240 miles east of Cape Town, may have been the only place that remained habitable during the devastating Ice Age, some scientists think. The sudden change in temperature wiped out many species elsewhere, around 195,000 years ago. Some scientists even believe that the human population may have fallen to just a few hundred individuals. Homo sapiens' evolution, then, was very likely strongly affected by the dramatic climate swings of the Pleistocene. These changes are believed to have presented powerful new natural selection pressures. Many animal species were driven to extinction by the advancing and retreating ice ages. Homo sapiens may well have survived, it would appear, not because of our big brains and capacity for innovation, but primarily because a handful of individuals were lucky enough to find a not-so-cold patch in southern Africa. They may have been able to survive because of rich vegetation available in the area. Although many other explanations for their extinction have been suggested, Neanderthals, with whom our species shared the planet until just before the last glacial maximum, 20,000 years ago, may have struggled to survive as the rising and falling ice ate away at their habitat, and unlike Homo sapiens, failed to find sustainable habitats. Variability in Earth's early environment, then, may have been the biggest challenge to Homo sapiens' evolution and survival. These repeated, dramatic shifts in the environment challenged many species, and may have actually selected for the features that ensured survival and have come to typify Homo sapiens, like the ability to alter our immediate surroundings in face of a growing threat. The evolutionary survival selection factors mentioned previously may have included the ability to respond to those changes. These environmental events would have put immense pressure on early humans. As noted above, it seems that early Homo sapiens were just barely able to survive these changes. Although early humans had the advantage of being in the southern hemisphere, in Africa, during some of the Ice Age, which afforded a somewhat less harsh habitat in which to survive, there are those who think they were able to survive these extreme conditions only through cooperating with one another. This may have led to the formation of close family groups or tribes, and the development of some of the modern Homo sapiens behaviors we are familiar with today. Humans would have had to develop new cultural technology to deal with cold environments and changing food sources, especially during the last 250,000 years. One of the greatest problems in the cold regions would have been the relative scarcity of plant foods to eat during the winters. In response, Homo sapiens would have had to become more proficient at hunting, especially the large animals that provided more calories. This in turn would have required the development of more sophisticated hunting skills, as well as better weapons and tools. These changes